Welcome to the lecture 26, and we'll continue with motion of charged particle in the electromagnetic field. So in last class we were in process of writing the Lorentz force, in particular the x component of Lorentz force, and we are trying to see whether it can be written in terms of some potential energy term. We will continue with this calculation. So let me get back to the last equation which we obtained. So Lorentz force Fx, x component of Lorentz force, the charge of the particle minus del phi del x minus 1 over c del Ax del t plus 1 over c del x of v dot a, this we obtained last time. So whether we can write this in a nice form. So let me show you. This can be rearranged. This can be rearranged q times minus del x phi times v dot a by c, and then ddt of del Vx of phi minus v dot a by c. So let me first calculate and show that this term can be written, this equation can be written in this form. So let me convince you. So the second term, let us first concentrate on second term. So phi is function of, that I mentioned, phi is function of x, y, z and t. So del Vx of phi will be 0. Okay, so this term is 0. Then this v dot a term will have Vx Ax term, and so you will have del Vx of v dot a is equal to Ax. That is clear, because it will have Vx Ax plus Vy Ay plus Vz Az. Now you are differentiating with respect to Vx, so it will be give you Ax, and this by c, so 1 over c Ax. So this whole term is nothing but minus 1 over c del Ax del t. Okay. So this whole term is written like this. Okay. And in the first term, so let us consider first term, we had already del phi del x, and already this term is there. So they are combined. Okay. So that is a very nice result, that you can see that we can write the x component of the Lorentz force exactly in the form let me write exactly in the form that f equal to minus del u del q plus ddt of del u del q dot of u. Okay. So now the Lorentz force, so conclusion is that we have written in terms of only x component, but from this result I can conclude that Lorentz force can be obtained from a potential u, which is phi minus v dot a by c. You can multiply it by q, so q times this. So this will be our potential. Okay. So we denote this q times this as our u. So this is our u. So you can. So Lorentz force, that a charged particle face in the electromagnetic field, can be obtained from a potential exactly in this form. and in this form we have seen that this D'Alembert's equation can give rise to the matches with Euler-Lagrangian equation. So immediately we can write that Lagrangian of a charged particle in the magnetic field will be T minus U form. So it will be T minus Q phi, the scalar potential, plus Q by C V dot A. Okay. So what will be the Lagrangian of a charged particle? So if I write explicitly, of a charged particle in the EM field produced by the vector potential A and phi is then Lagrangian is kinetic energy. Let me write now half m x dot square plus y dot square plus z dot square minus q times phi plus q by c. Now V I will write x dot ax plus y dot ay plus z dot az. Okay. So this is the Lagrangian for a charged particle in the electromagnetic field with in terms of potential. So we have obtained the Lagrangian for a charged particle in the electromagnetic field. So now let us consider a simple example and how to write and Lagrangian for a simple situation, and then we will move to that whether this Lagrangian is correct or not. So suppose if you have a charged particle in the magnetic field. So if you have a charged particle with charge q in the magnetic field. So example, charged particle in the magnetic field B equal to say uniform magnetic field along z direction. Suppose in the z direction you have a constant magnetic field B0. So find the Lagrangian for this. Okay, this is a constant magnetic field, there is no electric field. So we first can conclude that phi equal to 0, and we have to obtain the vector potential A such that B equal to curl of A. So B0 k will be curl of A, so you have to find. For a uniform magnetic field, A can be obtained as half B cross R. R is the position vector. So so using this formula you can very easily, otherwise you have to solve this equation to find A. Okay. So now A will be for this is for uniform, one can prove that for uniform magnetic field. So this is true for uniform magnetic field. So A equal to half. Now B is B0 k cross R xi plus yj plus zk. Okay. So you can very easily calculate this, and you will find that k cross I is j. So B0 x by 2 j, and the second term k cross j is minus I. So this will be minus B0 y by 2 I plus this plus 0, k cross k will be 0. So, we obtain in the potential, which is, if I write x component like this and y component x by this, and 0 is this vector potential produces a magnetic field B equal to B0 k, the z direction magnetic field. Okay. So, that you know. Of course, as you have learned already, there will be many, but at least one vector potential you have found. So, I can write my Lagrangian now. The Lagrangian for this particle in the z direction magnetic field will now be kinetic energy term will be as it is. So, let me write as T, which is half m x dot square plus y dot square plus z dot square. So, that I am not writing. Phi is 0. So, that will be 0 plus q by c. Now you have x dot a x, right. So, x dot a x is your minus b 0 y by 2 plus y dot a y is b 0 x by 2. Okay. So, your Lagrangian will be T plus q by c minus b 0 y x dot by 2 plus b 0 x y dot by 2. So, this will be your Lagrangian for a charged particle in the z direction magnetic field. But later we will see that there will be many potentials. So, we will come to that issue, and for each potential you will find one Lagrangian. So, there are so as we already know, there will be infinitely many A related by gauge transformation. There will be infinitely many A related by gauge transformation. So, in principle, there will be infinitely many gen for the system. So, we have found one Lagrangian. So, let us write down this Lagrangian is L1, because we will come back that how many infinitely many Lagrangian will describe the same dynamics, that point will come. So, when we will find another vector potential, so let us write this as A1. So, when we will find that another A2 which is related to A1 by gauge transformation, we will find our L2. When we will find A3, another potential, we will find L3. So, this point we will do later, but before that, the Lagrangian we have derived from the Lorentz force, whether this is a correct Lagrangian or not, that we have to check. So, for that, the way I mentioned in the very beginning, that a Lagrangian will be the Lagrangian of a system if it correctly produce the equation of motion. So, we have to check whether this Lagrangian can produce the equation motion for a charged particle in the electromagnetic field. So, let us verify that. So, once we verify that, then we will claim that whatever Lagrangian we have obtained is the correct Lagrangian. So, let me start with this Lagrangian we obtained. Lagrangian, let me write explicitly now, m x dot square plus y dot square plus z dot square minus q times phi, which is function of x, y, z and t, and then q by c you have x dot a x, which is also function of x, y, z and t in general, plus y dot a y plus z dot a z. I am not writing a y and a z detailed function, but it is understandable. So, this is my Lagrangian for a charged particle in the electromagnetic field. So, we have to find equation of motion. So, let us find equation of motion. Okay, that we know. Equation of motion means Euler Lagrange equation. Okay. So, first we will calculate del L del x dot. So, what will be there? So, from first term from here you will get m x dot, then x dot is here. So, you will get q by c a x, this is your x dot. So, in two places you will get your x dot. Now, if I find, so let me write this d dt of del L del x dot will be m x double dot. So, let me write x double dot plus q is the charge constant c and dAx dt. Okay. Now, the second part of the Euler Lagrangian equation del L del x, we should find where are the x dependents. No x dependent in the kinetic energy term. So, first x dependent from the phi. So, we will write minus q del phi del x. Then I have x dependent in all x, l, y and z. So, let me write q by c x dot del a x del x plus y dot del a y del x plus z dot del a z del x. So, what is the equation of motion? Equation of motion will be m x dot plus q by c dAx dt minus. So, I will write, so let us write the other side, because that I will do, q times minus q del phi del x plus q by c x dot del x del x plus y dot del a y del x plus z dot del a z del x. Okay. So, this, let me take this term also in the right side. If I consider that, so it will be m x dot equal to minus q, let us take outside, minus q plus q I take outside. So, 1 over c dAx dt minus del phi del x, q I have taken outside. So, 1 over c x dot del ax plus y dot del a y del x plus z dot del a z del x. Okay. So, I have taken q outside, and the right side I have taken all expression in the right side, and if this Lagrangian is the correct Lagrangian for electromagnetic field, we expect this quantity to be our x component of Lorentz force, that F equal to, so let me write we expect, then we will call that this Lagrangian is a correct Lagrangian. If we do not get, then there is some problem with the Lagrangian. So, F the Lorentz force, let me remind you again, this will be, so let me write x component will be x component plus 1 over c v cross b of x component. So, in terms of field, it should be q del phi del x minus 1 over c del ax del t, yeah, and then 1 over c v is let me write, okay, v cross b x component. So, I am not writing in details, but v cross b x component we have calculated earlier, you can find that. We will again what we will do, we will replace this term in the partial derivative term. So, we will use this equation in the last lecture. If you recall that 1 over c dx dt term is basically 1 over c del a x del t, the chain rule of differentiation, because a x is function of x, y, z and t. So, it is first I differentiate with respect to t, and then I differentiate del a x with respect to x, and then it will be v x. Similarly, del a x differentiated with respect to y, v y, plus del a x del z, v z. So, this will be the ddt of dx. So, I will substitute in the expression of the mx double dot, the right hand side of mx double dot. Okay. I forgot to put some equation of motion, equation number, but that will be helpful, but we can understand this. Let us write the mx double dot equal to q times, so 1 over c I will write now. So, minus del phi del x, let me write first del phi del x, then 1 over c del a x del t minus so 1 over c del x del t. So, and then 1 over c del x del t, then 1 over c I will write v x del a x del x plus v y del a x del y plus del v z. So, v z del a x del z. Okay. And there is a remaining term. So, let us see the remaining terms. Remaining terms are here. So, we have 1 over c, x dot is your v x. So, v x del a x del x plus v y del a y del x plus z dot is v z del a z del x. So, now we expect some cancellation. So, let me see whether I have written correctly. So, this is plus term and the earlier term is minus. So, we expect, so let us mark the terms which cancel. So, there is a minus sign here. So, v x del x x, v x del a x. So, this is minus sign, this is plus sign. So, this will cancel with this. Okay. And then next cancellation we will see v y del x, v y del x del y. So, it is not cancelling. V z del x del z, v z del z del x. So, this is also not cancelling. So, I think only one term will get cancelled, which is v x. So, let me check. So, only one term will get cancelled. So, nothing no other term will cancel, because other terms we will see what will happen. Okay. So, this. So, only one term will get cancelled, that this term. Okay. So, now your m x double dot is q times minus del phi del x minus 1 over c del a x del t. Okay. So, naturally you can see this is your E x. Okay. This is your Ex, x component of the electric field. If you recall the definition of electric field in terms of potential, this is grad phi minus 1 minus grad phi minus 1 over c del A del t. So, this x component will be. So, we expect that the remaining term will be V cross curl of A x component 1 over c. So, if we get that, and then you are through. So, this term we have calculated in last class, or we can see that this term is exactly these 4 terms. Okay. So, let us to convince you, let us calculate. So, first I will calculate V cross B. So, V cross B, and then B will substitute from curl of A. So, V cross B. So, if I write I j k, I am repeating this exercise. So, V x, V y, V z, no, B x, B y, B z, right. So, it will be x component V cross B x component. So, x component will be, so x component will be V y B z minus V z B y. Okay. X component will be this. Now, we have to find B z and B y component, and then we will substitute to get back. So, let us B is curl of A. So, again I j k del x del y del z, and then you have a x, a y, a z. So, if you calculate this determinant for B z and B y we need. So, B z will be del A z del x minus del A x B z will be B z will be a y by x a y, and B y will be del A x del z minus del A z del x. So, now let us calculate what is this quantity V y B z minus V z B y, which is the x component of V cross B. Now we have calculated this. So, V y B z will be del A y del x minus V y del A x del y, and V z term will be minus V z B y will be del A x del z plus V z del A z del x. Now, this is the term is your V cross B x component. Okay. So, now let us match in the term in the equation. So, for we have a term positive sign V y del A y del x. So, V y, remember V y del A x del y del x. So, V y del A x del y. So, this is the term matching with this. Okay. Now, there is a term minus V y del A x del y. Okay. So, del V y del A x del y. So, let us see whether this term. So, let me write this term V y del y del x, V y del y del x, this term is matching with this, and this term V y del A y del A x del y with a minus sign V y del y del x. So, this is matching. Okay. So, other two term also will match. If there is a sign problem, then it may be my calculation here, but there is no problem. So, conclusion is that, and I will conclude in 1 minute, that the Lagrangian we obtain half m x dot square y dot square plus z dot square minus q times phi plus q by c v dot a, this Lagrangian correctly produce Lorentz force law through Euler-Lagrangian equation. Okay. So, the Lagrangian we have obtained is the correct Lagrangian for equation of motion. So, I will stop here this lecture. The next lecture we will see there will be many Lagrangian for a charged particle in the electromagnetic field and their equivalents. Okay. So, bye for this lecture. We will start next lecture with this Lagrangian, and we will show you there will be infinitely many possibilities for such Lagrangians. Okay. Bye.